In the last video, we discussed blowups. The discussion was pretty abstract. In this video, we're now going to see some concrete examples of blowups to get a better feeling for the definition. To get the boring stuff out of the way, let's see a first trivial example when we blow up at exactly one function, r equals to 1. So if you recall, then x was an affine variety. And then this blowup x tilde was contained in x cross pr minus 1. So in this case, x cross p0. P0 is just a point, so this is actually just x. So x tilde sits inside x here. And then what we did was we started with the graph gamma f of the function f. Well, in this case, the function just goes to this point. So gamma f is actually just equal to its domain, u, which was just x minus the vanishing locus of this function f1. And so this sits inside, this u, of course, sits inside x, and then also inside this product here. And then by definition, the x tilde was just the closure of this u. So in other words, well, we go to this open subset u, and then we take the closure again. And then, well, there's kind of just two possibilities. So let's say if x is irreducible, then if this function f1 is non-zero, well, then this u is a non-empty open subset of x. And so its closure is everything. And so we get back x tilde equals to x. On the other hand, if f1 is 0, then u is the empty set, and taking a closure, you still get the empty set. So in this case, for r equals 1, really nothing interesting happens. We just either get the variety x back, or we get nothing, at least if x is irreducible. So more generally, we now want to look at the more interesting cases. And there we want to give explicit descriptions of the blowup. And, I mean, the definition involved taking some subset and taking the closure. This is not very explicit. Now we want to describe this with some concrete equations. And the next lemma at least helps us to understand what equations describe the blowup. Namely, if x is affine and the f1 up to fr are functions on x, then this x tilde, the blowup of x at the functions f1 up to fr, well, we know it sits inside this product x cross pr minus 1. And the lemma says, in fact, it sits as a certain subset of this product, namely the subset of coordinates x, comma y. Notice x are some affine coordinates on the affine space containing x, and y are the coordinates on this projective space. And the equations cutting out this subset here are exactly the equations yi times fj of x equals yj times fi of x for all pairs I and j in these in the corresponding indices 1 up to r on pr minus 1. Okay. So notice, first of all, our claim is that this here is a closed subvariety of this product here. It's described by some equations, and here we have to be a bit careful because, I mean, we have seen if you have an affine variety and we cut out some equations, you get a closed subvariety. If you have a projective variety and you have some homogeneous equations, then you get a closed subvariety. But this here is a kind of strange situation. It's a bit mixed, right? This is affine and this is projective. And we haven't really done a formal treatment of this, but what you can do in this case is, if you want to check that this is a closed subset in Zariski topology, then what you can do is you can cover this pr minus 1 by open subsets, which are affine, and then we're back in a nice situation, and we have affine cross affine, so this is an affine variety, and then you can check that that this is really a well-defined closed subset in there. So that's something that you could check for yourself. And so now let's see how the proof works. So why are these equations here satisfied? Well, if you recall, U is the complement of this vanishing locus of these R functions. And then all inside this graph here, all of the points of this U cross PR minus 1 satisfy that the second coordinate, so the kind of image coordinate, is just given by this vector f1 of x up to fr of x, and this is an equality in p r minus 1. That was basically just a definition of this gamma f. And then you see, once you have such an equality of vectors in projective space, then we always have this kind of cross product is equal to 0 pattern, right? So then we have yi times fj is equal to yj times fi. And so this shows that on the graph gamma f, all of these equations hold. And then if you take a closure, that's kind of a general pattern in algebraic geometry. If you have an algebraic equation holding on some set, and then you take the Zariski closure, then it still holds on this closure. The closure of this U isomorphic to gamma f is all of x tilde. So the equation still holds. So the x tilde is contained in this locus. And here again, you see I waved my hands here a bit and said, well, if the equations hold here, then it also holds on the closure. If you want to really check this formally, then you should go to these affine patches x cross ui inside this projective space. And then on the affine coordinates there, you can check that this really defines equations in the coordinate ring of this affine variety. And so on there, it is closed. And I mean, from now on, I will start to not always give all of these details, because that's somehow the standard in algebraic geometry. So you should really check this once carefully for yourself, and then get used to these kind of more interesting situations when you mix some affine variety and some projective variety. Okay, so we see in this lemma, we only get some kind of containment here. X tilde is at least contained in here, but we're not sure at this moment if it's always an equality. What we will do next is we will look at kind of most important example, I would say, of a blow-up, namely the blow-up of affine space at its coordinate functions. And there we are going to see that we get an equality. And so this is the next, yeah, this is this here. We take an, and this of course has a nice set of n, r equals n functions, namely the functions x1 up to xn. And so if you believe the lemma, then this is contained in this locus here in the xy, such that, and now we plug in fj equals just xj, and then we get the equality yj times xi is equal to yi times xj. Right. So this thing here, we call it z. This is a closed subvariety of this product. And then the big claim here is that this inclusion is an equality in this case. So we get an explicit description of this an tilde. It's cut out by exactly these equations. And to do this now, we do what I proposed here above, namely we do go to one of the affine patches. So let's look at just a single one. The others work similarly. This kind of U1 is now the set of points in Z. So we're going to really look at Z for now, of points where Y1 is non-zero. And this sits inside, so this is inside an cross an minus 1. And it has affine coordinates given by x1 up to xn. And then, well, being in this patch where y1 is non-zero, then we set y1 equals to 1. And the other coordinates are then given by y2 up to yn. We have these 2n minus 1 coordinates. And we claim that basically, well, the set of equations that we have, we can solve it. Namely, if we give x1, y2 up to yn, these are now n coordinates, then if you look at concrete examples of these equations here, namely we specialize to the case I equals to 1, right? Then on this side here, the y1 is equal to 1. And then we see the equation just says that xj here is equal to yj times x1. And you see both of these are given by the coordinates that we input. So somehow we see that we can solve these equations and get the remaining coordinates yj for j equals 2 to n from these equations, first of all. And then you see this was just the subset of the equations, right? This was the subset where I was equal to 1. But in fact, if we set xj to be this value, then we claim that the other equations are also satisfied. That's just a short check because you start with kind of, let's say, yi times xj. Then you plug this, this formula in, and you get this here. And then you combine it in a different way. You combine these two here to get the yj times xi. So you see this also gives all the other equations, so the remaining equations are satisfied. And so this means that this map here from an into this u1, which sends these coordinates that we give ourselves to, well, the first coordinate we keep, and then the x2 was equal to x1 times y2, and so on, up to xn, which is equal to x1 times yn, and we record the other coordinates y in the second factor. The claim is then, or what we just showed here is that this here is an injective and surjective map. So we have complete control over what this u1 is. We see this patch of z is just isomorphic to an. And this works in a similar way for all the other patches. And so this shows that this variety z is covered by these patches u1 up to un, which are all isomorphic to an. And we see that all of these are irreducible varieties of dimension n. And we have this condition that their overlaps are non-empty because, for example, well, you can check that this vector where you set all of the coordinates to be 1, this satisfies all equations. So this is contained in all of them. And so by the result, which we have used a couple of times now, z is also irreducible of dimension n. And, well, we know by the lemma, z contains the blow-up that we're interested in. And then, well, what we have seen is that the blow-up of an irreducible variety is always irreducible because it is the closure of this irreducible set here. And on the other hand, we know that for an irreducible variety, we can compute its dimension as the dimension of any non-empty open subvariety. And we can take, well, this non-empty open subvariety. We know that the blow-up always leaves u invariant, so this is still contained in there. But, well, the dimension of this is then just the dimension of an, so it's just n. So here we're basically using that an, or that this blow-up of an is a birational map, and then the dimension is a birational invariant. So we know the blow-up doesn't change the dimension. Okay, and what has this all given us? Well, we have this here, and because it was defined as a closure, it's still closed in here. So we have a closed subvariety. This is irreducible of dimension n. This is irreducible of dimension n. And so the claim is this forces this to be an equality. If this was a strict inclusion, then, well, you have here a chain of n inclusions of irreducible sets, and then this here would prolong the chain by one more strict inclusion, which would show that Z has dimension at least n plus 1. This gives a contradiction, so we have to have an equality. And this finishes the proof. This is what we wanted to show. And you see, this is, I would say, kind of cool application of this topology and of the dimensions, because when we started here, this here is a statement which has nothing to do with dimensions, right? It just, or somehow the claim that this is an equality, this is just a claim of an equality of sets. But we actually proved it using dimension as a tool. So I think this is pretty cool. And let's see now this blow-up morphism. Let's describe it a bit more in detail. So we have this blow-up morphism, an tilde going to an, and we know on the complement of the vanishing locus of all these functions, x1 up to xn, so in other words, on the complement of the origin, this is an isomorphism. So this also shows that this is a birational map. And then if you recall, we had this definition of the exceptional set. And the exceptional set was just take exactly this vanishing locus of all the functions, so take the origin, and see what lies above it. What is the pre-image under the blow-up morphism? And so if we look at what we just proved, this Z, this would cut out by these equations here. And so if you set the vector x to be 0, then you see both of these sides vanish. And so in fact, the equations are satisfied whatever value of yi's you choose. So in other words, the pre-image is just given by these pairs 0, y, where y is any element in this projective space. And so we see the pre-image just isomorphic to the projective space Pn minus 1. So the exceptional set is given by such a projective space. And the upshot then is, what does the blow-up do to an minus? What does the blow-up do to an? It leaves the complement of the origin unchanged and replaces the origin by a projective space of dimension n minus 1. Okay, and so how should you imagine this? What picture should you have in mind? So here I copy these very nice pictures from Gartmann's notes. So you could imagine, and that's unfortunately the wrong picture. What does the blow-up do? It starts with an, there's the origin, and then it plugs in an Pn minus 1. So in the case of n equals 2, you start with the plane and then you plug in a P1. And you could imagine this you just kind of stick it in, and then you have a P1 which meets this here in a single point. Unfortunately, this is not the right picture. To get a better feeling for the right picture, actually a nice thing is to look at this construction of strict transforms that we had before. So the idea is, inside this A2, you have the origin, and then you look at lines through the origin, right? From every direction you can approach this point here. And then let's see what the strict transform of the lines is. And we're going to see in a minute why this is a good idea. Okay. So let's see for a given line L, which is just kind of the set of lambda v1 up to lambda vn, where v1 up to vn is a non-zero vector. We have this line inside A2. And so the question is then, what is the strict transform of this line? Well, we go to the restriction of the line to the open subset U away from the origin. So this would be the same set, but now we set lambda to be non-zero. And then we go into this product an cross Pn minus 1. And if you recall, the graph then just takes this here, and because the functions are very easy, it's just the map which sends x1 up to xn to x1 up to xn. You just get the element of the projective space Pn minus 1 given by this same vector here. But now, well, Pn minus 1 is invariant under scaling. And so, in fact, you can get rid of these lambdas and just, you see the element of Pn minus 1 that you get is independent of lambda. You just get, for example, this vector v1 up to vn. And so now you see this is a subset of an cross Pn minus 1. Here, the first coordinate varies as lambda varies in k minus the origin, but the second coordinate is actually fixed. It's just always the same vector. And so if you take the closure, well, then the second coordinate still remains fixed. And here, instead of only allowing lambda non-equals to 0, you allow arbitrary lambda and k. And so in this very easy case where we take the strict transform of a line which is just isomorphic to A1, we can just do it. We just get, again, something isomorphic to A1. And you see in the picture, you start with a line, and then you basically transport this line to some fixed position where you fix the second coordinate to be just some point in this projective space. And in this case, you see you start with A2, and then the second coordinate is a P1. And so basically in this picture, this kind of up and down direction, this is the P1 direction. And so for the given line L, we kind of transport it and we set it at the fixed height, at the fixed coordinate in this P1. And you see different lines will have different coordinates in this P1. And so basically for every point in P1, you get a line, right? That's the whole point of P1 is a set of all lines in A2 to the origin. And so basically for every height coordinate here corresponding to a point in P1, you just get the strict transform of the corresponding line. And these lines then sweep out this this blow up. And then we understand that the preimage of 0 is then exactly 0 cross P1. And it's exactly the kind of P1 which parametrizes all of these directions to the origin. And that picture generalizes if you have AN here, then this sits inside AN cross PN minus 1. And this exceptional fiber, Pn minus 1, then exactly parametrizes all the possible choices of lines through the origin inside AN. And the cool thing, the final thing that I want to remark is, you see, if you pick a line L1 and a line L2 in here, then of course in A2 they intersect exactly at the origin. But their strict transforms L1 and I guess this here might be L2, you see they are on different heights, so they no longer intersect. So this is a kind of an important slogan to keep in mind, that if you have lines to the origin here which meet before you blow up, then their strict transforms in this case will no longer meet. And that's often a very useful thing to do. And so this was the example of blowing up affine space in the origin. And we're going to see this is not just a very special example, but in fact, many blowups can be reduced to this case. And this we're going to see in some of the next videos.